So how do you create a phylogenetic tree? And then this is what we're going to talk about for the next little bit. The point of this really is just to prove to you that this isn't magic. There's a tendency to look at phylogenetic trees a lot like people look at crystal structures of proteins. It's like, it's perfect. You know exactly what the structure is, down to the nanometer, and nobody ever questions a protein crystal structure. Likewise, nobody ever questions phylogenetic trees. And I want to show you, first of all, that there's not magic. It's a mathematical transformation of numbers. There really isn't. It's a graph that shows the relationship between sequences. That's all it is. But they're also fallible, or they have limitations that you need to learn a little bit about as well, just like a crystal structure does. How many of you guys have seen good crystal structures of proteins? I was really impressed. Years and years and years ago, I saw a crystal structure of ribonuclease A grown in a sounding rocket in zero gravity. Beautiful crystals. You could see the holes in the tyrosine rings in these crystal structures. Completely bogus. Because if you take that same crystal structure and now put it in a molecular dynamics simulation, add water and make it at room temperature, you watch it sit there and jiggle and wiggle and twist around and all that kind of stuff. That's what molecules look like. Not some rigid, exactly, here's a hydrogen bond down to the 10th of a nanometer. And the same is true for trees. Trees are graphs showing relationships and not anything else. There are several steps in the construction of one of these trees, though. We're going to go through in the next couple of days each of these. First of all, you have to decide what sequence to use in an analysis. It turns out that some sequences are better than others. You can create a tree based on any sequence. But the meaning of it and the reliability of it depend on what sequence it is and how you manage the data. And there's a gold standard, and there's some other stuff coming out of the block. You have to actually get those sequences. These days, that usually means going to GenBank and fishing them out. But it can also mean having to go into some DNA, doing a PCR experiment, and getting something sequenced. You have to make a multiple sequence alignment of them. Since you're creating phylogenetic trees, what you're doing is you're comparing homologous things. And what a sequence alignment is an assignment of what residue is homologous to what. That's what we're going to talk about today. The next part is to do some mathematical transformations to take that alignment and convert it into a graph showing the relationship between sequences. And there are several really good algorithms for this, and also some not so good. And then lastly, you've got to look at that tree and interpret it. And this is probably the most important step, because this is where you're most likely to go wrong or not see that you've gone wrong. And we're going to go through this theoretically, and then I'm going to follow up with a real example of an organism now called Eubacterium thermomarinus, and show an example of why this can be a very useful process.